So in this lecture, we're talking about relative maxima minima. So let's see B in the point of the domain f of x. So a local max or minima at C with the value f of C, if f of C is greater than f of x for all x near C. And a local minima at x equals at C with value. So if you're the highest point in an interval, you would be a local max. And if you're the lowest, you're a local minimum, essentially. That's all it's trying to say. Not every critical point is a local max or a local min. That's key. That's key right there. So then, if you have f of x equals x cubed, then f prime of x equals 3x squared. And the critical point would be x equals 0. But we can see that it's neither a max or a min at x equals 0. It's not. So that proves our point that not every critical point is a local max or a local min. So we talk about the first derivative test. And that's a critical, play on words, critical for us to know. It's called the first derivative test. So let's see the critical point of the function f of x. Then, 1, if f prime of x goes from positive to negative at x equals c, positive, negative, there must be a local max. If it goes from negative to positive, 0, goes from less than 0 to greater than 0, we have a minimum. Logically, you can see my arrows. If it goes up, then down, it's a maximum. If it's down to up, it's a minimum. And if it remains the same, equals neither local max or min. So let's look at some examples, because that's what's going to teach us this concept of local extrema. Because it's not that bad. We just have to know how to find our first derivatives. That's all we have to do. Because if f of x equals e to the x squared, obviously, if we find f prime of x, which equals e to the x squared to x. And that's 0. This will never equal 0, by the way. It's 0 at x equals 0. So we're going to put a line at 0. And I'll put a, like, -1. Would still be positive, so it'd be negative, though. And positive on this side. So I did f prime of -1. F prime of 1. And that means we go from negative to positive, so we have a minimum. That's what I should get. So x equals 0 is a local minimum for this one right here. If you have f of x equals 3x squared, sorry, if f of x equals x cubed plus 9x squared minus 21x plus 86, and f prime of x equals 3x squared plus 18x minus 21. Then if I were to factor that, I get a product as product of -7, sum of 6, which is going to be 7, -1. So we get 3, x plus 7, x minus 1. So then I plot that on a number line. And I plot in those intervals. So if I put a value test around here, if I do something to the left of -7 in this derivative right here, such as -10, I would get a negative number here and a negative number here, which would give me a positive number. So I'd go going up and I'd have a positive derivative. Right after that, if I have something like -6, I'd have a positive, I'd have a negative value, and I'd also have a negative over here. And then something to the left, I mean the right of 1, like 10, would be positive. So that means you have a local max at this value. And still to the left, it's for a local max here and a local min right here. So there's a local max at x equals -7 and a local min at x equals 1. That was fun. I think we can actually go ahead and cover the next lesson as well in this video, which is going to be the fact that so we talk about global max. If f of c is greater than or equal f of x for all x in the domain. That's what a global max is. And then you go to global min, which is f of c is less than or equal to f of x for all x in the domain. That's a global min, and that's global max. So then they draw a graph, but if you have a closed interval, it's called closed because we're using square brackets. Closed interval of a and b. What happens is that we compute f of a and f of b, and then f of the critical points. That's what you do. so let's look at an example. If we have a parabola right here. So we have a parabola, have f of x equals x squared minus 2x. And the interval of minus 2, 2. What happens is that f prime of x is equal to 2x minus 2. And the critical points would be x equals 1. So if I test in the endpoints, then test in at 1 into the function, I get four plus 4 is 8. 0. Minus 1. So the global min. And global max. We're going to do one more example, one that's a little bit uglier, because the other one's not very, it's kind of redundant, the other one, so we're just going to do one more example. And if I have this, right? That interval, then f prime of x is equal to 4 minus 4. That's what we should be getting. And if I solve for the critical points, that would just be 0. Or actually 1. So because f prime of x does not exist at x equals 0, but the critical point also is 1. Because that would make 4 divided by the cube root of 1 is 4, 4 minus 4 is 0. So, and plus 0 is not even in this, well, no, 0 is this domain. 0 is in this domain, but 1 is not in this domain. So we do not count 1 because we have to look at the interval that we're given with to start off. So what happens is we test our critical points in our function, or our endpoints as well. And in our function, it ends up being, and you can do this on your own time as well. You should be getting something along the ballpark of 12 for this one, 2, and 3.78, meaning that this is the max global this is the min. That would be that one. Global min at x equals 0 and global max at x equals -1. So those would be the values.